Wei Xiong. So I see most of the audience are similar to yesterday's presence, but I'll just introduce for the sake of new audience. So Professor Wei Xiong is a full professor at UCSD, US. He is an expert in 2D IR spectroscopy. So he started his independent research career in UCSD in 2014. Then he is a full professor from 2022. So he's a Ken Wilson faculty scholar. So he has kindly agreed to give this set of seminars organized by DCS. So he is mainly focusing on the polytonic chemistry, how to understand this field. So yesterday he has given a fantastic tutorial on this topic. So where he introduced the topic, and today he is going to present some more advanced results or research-based talk. So I welcome you for this talk. So Professor Wei, you can start.
Thank you, Clyde. Okay, thank you for those of you coming for the second part of the talk. So today I will continue the topic on towards a rational understanding of proton chemistry. So to just review some of the things we talked about, proton chemistry is has a potential to be a new type of ways to control chemical reactions. And there have been quite several actually very interesting, beautiful research, such as one that actually Clyde also involved from the Emerson group, and also the works from Blake Simpkins group that I have already talked about. However, a burning question to the field is that do we actually have a mechanism that we can use to guide the designing principle for using proton to control chemical reactions? And so the important mechanistic question that I introduced yesterday was that, well, because we are in this collective strong coupling regime, we do need many, many molecules to reach to the strong coupling. As a result, the protonic state are actually the minority state in the system, where the dark mode are the majority. So a question is, how would those minority state in the cavity actually influence the chemistry, actually tilt the chemical landscape compared to the majority of the dark mode? And specifically, how would the molecular energy dynamics be influenced by proton or strongly coupled to the cavity? So we do need a tool to actually...
we can't see slides.
I think he has not started.
Sorry, I forgot to share. Good question. Yeah, but those are the old slides.
Thank
Okay.
you.
Yeah, thank you for reminding. Yeah. So so we do need a tool to distinguish proton from dark mode, as well as following the dynamics. And from there, I introduced the two-dimensional infrared spectroscopy. So through the tutorial yesterday, I showed you that proton, the 2DR can really help us to follow the energy or population transfer from protonic to molecular like dark mode. And also because of this order, that 2DR is able to also monitor the dynamics of the dark mode by themselves. And lastly, that we can also use anisotropy to follow the angle between energy transfer or different modes, which are all the tools I will use today to show you some of the examples of how to use in 2DR to understand ultra-fast dynamics of protons. So there are 4 questions I hope that I can go through with you, where the first question is, back a few years ago, we tried to ask this question: what are protons really good at? So intuitively, we thought that proton may be good at energy transfer because of the delocalization it brings in among participating molecules. And this is actually an issue in condensed matter chemical systems. For example, that it is long known that in most of the liquid phase system, a intermolecular vibrational energy transfer would simply not exist because of the dipole-dipole interaction between those vibrational modes are just so weak, so the energy would rather dissipate into the solvent system. And this can be seen by taking the tungsten hydrocarbonyl molecule that I talked about yesterday and its C13 isotope label version together. When we take the 2DR, you can see this set of diagonal peak where there is no cross peak between them at all, indicating there is no measurable energy transfer. So we wonder, by actually taking both of the tungsten hexavalent carbonyl and the C13 isotope label version and force both of them to be strongly coupled to the cavity. Can we use actually the cavity as a conduit to transfer energy from one molecule to another? So that was the idea. And then my former student Bo Xiang took this molecule and then stuffed it into the cavity mode. And now because we have two vibrational mode, together with the cavity mode, they can form a three-proton system, namely the upper proton, middle proton, and the lower proton. We can also take measure the dispersion curve as you see here, where the simplest way to model the system is through a 3x3 Jens Hamiltonian. And using this Hamiltonian and the dispersion curve, we can basically diagonalize the Hamiltonian and find out both the eigenvalue and the eigenstate, where the coefficient of those eigenstates, if you square them, we get the so-called half-field coefficient. And this is important. What this tells us on this plot is at a certain incidence angle, when we create a proton, how much of the energy would initially deposit into, for example, the tungsten hexavalent carbonyl, which we call donor mode, or the cavity mode, or the acceptor mode. For example, for the upper proton, when you excite it, the majority of the energy stay within the donor, where some of them, about maybe 1/3 of it, would go to the cavity mode, and there is a really small amount still going directly into the acceptor, where the middle proton is basically 1/3 for each of the branch, and the lower proton is the opposite. The majority of the excitation would go to the acceptor mode, where that only small amount would go to the donor. So we are interested in to see if by forming the proton or strong coupling with the cavity mode, we can mediate energy transfer from the donor to acceptor, or vice versa. When we took the 2DR, this is the example 2DR spectrum, we see a very interesting cross peak. So this peak appear as when we excite the upper proton, but after a certain time, it actually show up at the absorption of the lower proton. So precisely what happened is that when we excite the upper proton, the energy would stay on the upper proton for a while, and then it would transfer to the matter side of the lower proton, that is the energy acceptor. And now, if you recall that the upper proton mostly composed by the energy donor, therefore this peak can be interpreted as a signature of energy transfer. Similarly, this peak corresponds to that you excite the upper proton where the energy just simply relax to its own dark mode, that is energy donor. So these two peaks are important for us to understanding the mechanism of energy relaxation here. So although that we see, a really possible bright signature for energy transfer, we do need to be a little bit careful, because as I told you before, even when we excite the upper proton, there could be still a very small portion of the upper proton that directly end up into the acceptor population. So that is just an energy relaxation channel. So to see which one is dominating, so we need to go quantitative. So through half-field coefficient measurement, we know that the population ratio between the donor and acceptor, when we just directly exciting the upper proton, it's about 14:1. And when we do the peak intensity integration measurement, we found that those two peak ratio is about 14:6. That means there is a 6-fold of enhancement of the peak compared to if it's a simply energy relaxation process. So and furthermore, when we track actually the dynamics between these two peaks, you can see for the energy relaxation peak, it rises up really, really fast and then just simply start to decay. Where for the energy transfer dynamics, it actually rises much slower and take a while to actually rising up, simply indicating it takes the photon multiple bounces to actually transfer or relay the energy from the donor to the acceptor side. So from both of the evidence, we say that this is a clear evidence of a new intermolecular energy transfer channel is enabled between the donor and acceptor through the strong coupling mechanism. So this would be the first example that I hope to show you. that what polariton are really good at to do. That is, under strong coupling, it can enable vibrational energy transfer between molecules. The second question we want to answer is then, so what? How it can actually influence chemical reactions. So as we want to move to the side of chemical reactions, we start with actually learning from the literature. For example, this is an example review paper that published by those folks summarizing by then all the available chemical reactions people have demonstrated that can be influenced by strong coupling. So when we study this, we realize many of those beautiful examples are a little bit more complex, such as that they are not a elementary reaction, but a reaction involving multiple steps. And there are some reactions also diffusion limited, I believe is perhaps this one. So we want to just simply take one step further to study a very simple reaction. So we were looking for some example of elementary reactions. And in the ultra-fast dynamic world, there indeed is a very elegant example, which is the pseudo-rotation of this iron pentacarbonyl molecule. So this molecule has two types of carbonyl mode. One is this axial mode that is involving these two carbonyl. The other is this equatorial mode that's involving those three carbonyl mode. And as you can see from this cartoon, that the axial mode that can actually band towards to each other to form, the new equatorial mode and vice versa. So as a result, it appeared to be a rotation of the molecule about 90 degrees. However, this is really not what happened. What happened is that through the ligand rearrangement, the molecule would overcome a small barrier about 2 kcal per mole. So that, as you can see, this barrier crossing event really mimic a elementary chemical reaction. Except that for both the reactant and the products, it's the same chemical. So, but nevertheless, it actually captured the essence of elementary reaction. And this compound indeed has been studied by Chuck Harris group back then in Berkeley long time ago. What they did is that they first showed that for both the axial mode and the equatorial mode, that they have characteristic vibrational frequency. And as the A mode and the E mode undergo the pseudo rotation and exchange their character, it is equivalent for one mode carry the energy from its original mode to the other mode. So this is a chemical or energy transfer event. And as you know that a energy transfer would simply bring the initial excitation and transfer the energy to the other mode and creating this cross peak. So by following the cross peak, Chuck Harris group could actually learn about pseudo-rotation dynamics. And what we simply want to do is to put those molecules inside of the cavity and see how they would actually, by strongly couple to the cavity, how it would influence the chemical reaction. So back then, my former postdoc, Tengteng Chen, and grad student Mo Yang prepared the sample in collaboration with a series student from Howell's group, Matt Du, where again that we're dealing with a now single molecule has two vibrational mode, that is the axial mode and the equatorial mode. They again can still form a three polariton system, upper, middle, and lower polariton. And as using the same argument, the upper polariton are mostly composed by the A mode, where the lower polariton are mostly composed by the E mode. And we are interested in to see an energy transfer between the A and E mode. So we could actually, again, using the cross peak between the upper polariton and lower polariton to follow the relevant energy transfer between the A and E mode. This time we did a little bit different. However, that is we also took advantage of the fact that we can see the dark mode. So we follow the dynamics of the dark mode involved in the system, such as I highlighted here using this gray box that correspond to an energy transfer directly between the A and E mode without involving the polytonic state. So the corresponding dynamic is summarized here. So let's take a look at the red scatter dot first. The red scatter dots are the energy exchange dynamics of this compound outside of cavity. So that was basically reproducing Charles-Harris's experiment, which we successfully did. And then, importantly, for the dynamics involving the upper polariton, that is the blue dots, you can see this reaction or this dynamics is accelerated precisely that compared to the one outside of cavity is enhanced about 30%. So change from 0.08 inverse picosecond to 0.11 inverse picosecond. But more importantly, that if we see these gray dots here, that is the energy transfer dynamics only involving the dark mode inside of the cavity. We find that the energy transfer dynamics is about 0.09. So it's quite similar to 0.084. So we basically say there is no difference between the one outside of cavity and the one of the dark mode. So this is very important because of this is the first time experimentally someone actually distinguished the dynamics between the polariton and dark mode. So we find that's very interesting. However, that's not the end of the story because as a spectroscopy, we know that there could be multiple channels that can lead to this cross-peak emergence. So I told you one that is about pseudo-rotation. However, the other one, as I'm sure many of you are aware of, is the so-called intramolecular vibrational energy redistribution, or IVR. It simply indicates that if we put energy into one of these vibrational mode, it may just unharmonic couple to a orthogonal mode. So this is a unavoidable channel in most of the multi-atomic systems. So one of the big questions that we had back then was like, well, is the cavity actually accelerating the pseudo-rotation or is it accelerating the IVR? We didn't know. So it took us a while to figure out, but there is indeed a quite elegant way to sort this out. So just bear with me a little bit. Let's take a look at the molecular frame of the pseudo-rotation. So you can see if the molecule start with the E mode, then the net dipole moment is pointing up in the molecular frame. And however, as it morphs into the axial mode, the A mode, even though that it changed its character into the A mode, the mode is still pointing up, which means that in this molecule, through pseudo-rotation, it undergoes a energy transfer between two vibrational modes that is parallel to each other. And that is radically different from the IVR process because by definition, IVR indicates that it's energy transfer between two modes that is orthogonal or perpendicular to each other. So if you recall about the tutorial of anisotropy, then you would realize that because of this is a energy transfer between two parallel modes, this is energy transfer between two perpendicular modes. Then we can use anisotropy to differentiate them. For the first case, that we would expect a anisotropy around 0.4. For the second case, we would expect a anisotropy around negative 0.2. So we went ahead, did the measurement of anisotropy, and amazingly, you find that outside the cavity, that the anisotropy indeed is positive. However, it doesn't start with 0.4. It starts with 0.06. What it tells us is qualitatively, we know pseudo-rotation dominates the dynamics. However, that is not the only channel. IVR indeed already exists over there. Where for inside of cavity, you see that the anisotropy is completely flipped. That is, however, is also not negative 0.2. Instead, it's negative 0.07. So what that tells us is that now the IVR become the dominating channel, where the pseudo-rotation become the secondary channel. So going through feeding these pseudo-rotation dynamics using a very complicated kinetic model, which I will not bore you here, we can further extract out the corresponding pseudo rotation rate versus the IVR rate. So as you can see, as we move the sample from outside cavity to strongly coupled to inside the cavity, we indeed can enhance the IVR by twice. As a result, the pseudo rotation is further slowed down by about 15%. So, and interestingly, after about 6 months, that Sharon Hemschafer's group performed a MD simulation on the same system, where they can also show by involving the upper polariton, it indeed can slow down the pseudo rotation dynamics compared to the one of dark mode and outside cavity. So we think what happened is that the actual energy that's been put into the cavity must have been act as a driving force to the pseudo rotation, probably through a low frequency mode here. However, as the energy transfer happened through IVR, it basically lost this additional driving force and then therefore slow down the pseudo rotation. However, this is an open question, actually. Should be further examined and also probably provide additional insights through additional theoretical and simulation study. Okay, so this is the second question or story I want to show you, that is how it would influence chemical reaction. The answer is that, well, through enable a intramolecular energy transfer, it can indeed impede competing dynamic pathways. However, very importantly, is that it confirms, well, polariton have this magic to actually change the course of chemical reaction. Dark mode do not have actually this magic power. It simply remains similar as the regular uncoupled molecular state. So that is the second topic I want to cover. And I want to emphasize one thing to bring the third topic. That is, through the first two quick examples I showed you, we carefully chosen some system that has the least amount of energy disorder. In other words, the system are as homogeneous as possible. And we did that for a reason, because of polariton is a topic that born out of atomic or molecular physics, and in there that all the molecules are usually prepared in the exact same way. So we want to follow or prepare those molecules with a very similar environment. However, as a chemist, we know that chemistry cannot avoid inhomogeneous broadening or inhomogeneity. So the next question that we want to answer is, what is the role of energy disorder or inhomogeneous broadening? So it was a natural evolution of the topic in my group, because of we also were puzzled by some of our own results and also research results from our friends in the community. So on the left side, what I showed you is also the dynamic of the pseudo rotation. We had this graph in the SI. So basically what we showed is that the red one is outside the cavity. The rest of three are all inside the cavity, strong coupled dynamics. But you can see only when, in the case of when we labeled high or medium, we see a dramatic change of the chemical dynamics. Where for the one that we label low, that is still above the classical strong coupling criteria, we did not actually see much of the modification of the dynamics. So we were puzzled why that's the case. It seems like in order to actually modify the ultrafast dynamics, we always need a coupling strength that is larger than the onside of strong coupling. And also from Kevin Kubarich's group back then at U Michigan, they studied some inhomogeneous broadened chemical systems strongly coupled to a cavity mode. And what they showed is that for the 2D polaritonic spectrum, the majority of the feature can be simply explained by measuring the molecular spectrum, and then you retrospectively apply a polaritonic spectral filter onto it. In other words, what they show is that the measured polariton spectrum is not very special in terms of whether it has any protontic feature, but instead most of the feature are coming from the underlying molecular state, and this was later also that confirmed through a simulation from Adam Duncan-Booker's group. So that already bring in a huge puzzle in my group, is because we know that the previous study I showed you, we indeed can see actually interesting dynamics of protontic states that cannot be described by a purely molecular mode inside of the cavity. But those are the homogeneous system. But when people actually start to actually study inhomogeneous system with energy disorder, they seem to see something different. However, that is a little bit, this realization was a little bit against one thing that the field has been actually take or believe, that is proton are robust against energy disorder. So again, that I showed you this very beautiful paper yesterday. So this is the paper that talking about how energy disorder would influence proton. And one of the conclusion they gave is that, well, the symmetry of the dark mode will be broken so that the dark mode will become a little bit bright. Another conclusion they gave is that the protonic spectral feature is also robust against the disorder. So that was what people have been taking from a really important message from this work. But it seems like all the ultra-fast data suggests a little bit different. So we went back to revisit this problem. Specifically, my current postdoc, Tianlin Liu, and also grad student Wu Xinyin actually went down take exploration of this problem. So again, they used the Tavis Cumming model with a little bit random inhomogeneous broadening or energy disorder to the system. And then they run the diagonalized Hamiltonian, run it multiple times, and then they see what's happened. So what they can show is, as they increase the energy disorder, that is a full width half max of the energy disorder of the inhomogeneous broadening, they can still see. So the proton spectrum, that is a red line here, remain to be proton-like, okay? Because you can see the Rabi splitting is remain the same. So it seems that agree with the PRA paper I showed you from the last slide. But there is a key difference that is shown on the lower panel here. So what we plot here is the wave function of the protonic state and the dark mode in both scenarios. So in this scenario, as you can see that, I hope that you can see that the wave function distribution of the lower proton is plotted as a vertical line here. What this vertical line indicates is that if I excite the lower proton, the excitation would be equally distributed among all those molecules that has a slightly different frequency. Okay, so that is a signature of delocalization, so as the upper proton. However, for the dark mode, you can clearly see if I excite a dark mode, the energy would mostly stay at the molecular mode that shares exact same frequency as the dark mode that I'm exciting. So that is a signature of localization. So the vertical line, delocalization, the diagonal line, localization. And that's the case of when the energy disorder is relatively small, about 24% of the Rabi splitting. But if you increase the full half max of energy disorder to be about 70% of the energy disorder, we see actually not only the dark mode are localized, so as the proton mode, they are also become much more localized compared to in this case. But importantly, as you can see in both scenarios, this here and this here, it still satisfies the strong coupling criteria. That is the full width half max that is smaller than the coupling strength. So what we show here is phenomenologically, if we increase the energy disorder, it seems to start to compromise the delocalization property of protons, which is one of the unique properties of proton state. We went down further, scan the full width half max of the inhomogeneous full width half max, as well as the Rabi splitting. And then we calculate or we characterize the delocalization using a parameter called normalized inverse partition ratio that people have developed it for study excitonic delocalization. But in short, that in our calculation, if this NIPR equals to 1, it indicates the polariton are delocalized. But if it equals to 0, it indicates the polariton are localized. So we find a very interesting plot. You do see that the polariton at some point would transition from a localized state into a delocalized state. However, this transition does not actually happen at the strong coupling criteria, which is this line here. So on this side, this is weak coupling. On this side is already strong coupling. But the transition indeed happened at a threshold that require the coupling strength to be three times of the onset of strong coupling. So as you see, this ratio become, instead to be 1, is about 0.3. Okay, so this is what we refer as the delocalization criteria. This is, of course, a simple prediction, from experimentalist using Taoist coupling model. So we want to see if it have any experimental importance and significance there. To test whether this is important or not, we want to find a chemical system that is a phenol system that can form hydrogen bond between different phenol molecules. So if it's in the dilute limit, then you would only see one peak because there is no chemical bond interactions between the phenol molecules. However, if we increase the concentration, you see that this one peak involved to a peak with the shoulder on the left side, and through a through MD simulation, we can confirm that this additional shoulder is actually coming from the hydrogen bonded complex systems. And it's very broad. Indeed, for both of the peak, you can see they are quite broad and Gaussian-like. So they actually represent the limit of inhomogeneous broadening or with a lot of energy disorder. So very lucky, then if we simply just lower the temperature of the system by about 10 degree Kelvin, this system crystallizes. Okay, and as it crystallizes, it forms these two very sharp and beautiful peaks through a variable temperature measurement, and also with the aid of MD simulation, we can assign these two peaks to be a single hydrogen bonded configuration at a higher frequency and the doubly hydrogen bonded configuration at a lower frequency. And already through the fitting, that you probably can see those two peaks are much more narrower and they are indeed Lorentzian. So those are the cases with very little energy disorder, or in other words, they are in the homogeneous limit. So we have in the same system, we have both inhomogeneous limit and homogeneous limit, and that is a perfect system for us to test the delocalization criteria. So we again taking, can take 2DR. This is the spectrum at 0 picosecond. At longer waiting time, you can already see the growth of the cross peak. So we follow those cross peaks to follow their dynamics, and we want to see what is the exchange rate. So for the solid case that we measure the exchange rate like this, we extract the number that is about 0.16 inverse picosecond, so about 5 picosecond of exchange rate. Where for the liquid phase, that is a little bit complicated because the ratio between the complex and the free is not 1-to-1. So from complex to hydrogen complex to the free molecule is about 1 picosecond, and the inverse is about 5 picosecond. So we characterize both of them in the inhomogeneous homogeneous limit and the inhomogeneous limit. But then it comes to the old question again: is this really a conformational exchange, or it could be an energy transfer? So with the conformational exchange, you simply expect that the chemical bond or the hydrogen bond would break between the doubly hydrogen bonded configuration to switch to the singly hydrogen bonded configuration, or vice versa. Okay, or in this case, that there would be involving no hydrogen bond breaking at all, but simply just energy would remotely transfer from one side to another through a faster energy or resonant energy transfer phenomenon. So the way to differentiate them, one way at least to differentiate them, is through deuteration, because by deuterating the change the level of deuteration of the phenol, we can literally change the distance between the energy transfer pair. And if this is a energy transfer phenomenon, then we would expect the dynamics to be heavily dependent on the level of deuteration. So we perform this experiment. As you can see in the solid case, the data nearly lay on top of each other. The gray dots are the more deuterated one, where for the liquid phase is also very similar. So we have those number listed here. The experimentally measured results suggest that the energy transfer channel is minimal here, where it is the conformational exchange dominant here. And this is also expected because of the average distance between the singly and doubly hydrogen bonded configuration in the either the solid or in the liquid phase, much longer than the Foster radius of resonant energy transfer. Okay, so this is all the dynamics outside of cavity. And again, what we want to do next is to put both systems inside of a cavity. By putting them into the cavity, because of we now again have two vibrational mode, so we will follow ideally three polyatomic mode. You can see the three polyatomic mode, that is the upper and the lower and middle polyton for the solid phase. Where in the liquid phase, because of the large inhomogeneous browning, you simply cannot actually see a visible middle polyton, but we can still see the upper and lower polyton. In nearly all the experiment, we try to keep the Rabi splitting between the lower and upper polyton to be the same, so that the dynamics are measured all in the same experimental condition, except that one is a homogeneous system, the other one is an inhomogeneous system. So the measured dynamics is summarized here. We can take a look at the liquid phase first. As you can see, the liquid phase dynamics, the dashed line is outside cavity, solid line is inside cavity, and this is the extracted dynamics. They are roughly the same. It's slightly different, but it's really within the error bar that we can measure. However, when we study the solid phase result, that is a homogeneous limit, we can see a rapidly acceleration when we actually strongly couple the system inside the cavity. It is again accelerated about 3 times. So that by itself is very interesting, and we still need to answer the same question: is it acceleration of energy transfer or conformational exchange? In this case, we cannot do the deuteration trick anymore, because as we change the deuteration, we will change the coupling strength. So we now resort back to the anisotropy trick that I told you before. So first, we performed some MD simulation, try to see what is the probability of energy transfer between vibrational mode at different angles. And through the simulation, as you can see, at each relative angle, they all have a pretty low probability, and it's nearly the same. So if you average them out to calculate the anisotropy, it would be the red solid line here. And the rest of the scattered circle here are simply the measured result, with the black line to be the average result. So as you can see, the anisotropy is nearly 0. So what that suggests us is indeed that now the new dynamics inside the cavity is dominated by energy transfer again. So I didn't show you here, but if it is indeed through energy exchange, if it's indeed through conformational exchange, the conformation dipole moment between the singly and doubly hydrogen bonded system would change about 120 degrees. So that certainly would start with an anisotropy that is non-zero. Okay. So very interestingly, if we keep changing the coupling strength for the homogeneous limit case, we totally did 3 experiments. You can see at relatively low coupling coupling strands, we also don't see any dynamic change compared to the one of outside cavity. But as we increase the coupling strands, we see a steady takeoff of the exchange dynamics. In contrast, if we study the liquid phase sample, the inhomogeneous limit, regardless how we change the coupling strands, the measured exchange rate basically stay within the error bar compared to the outside cavity. So we really don't see any of the effect. So the take-home message here is we can only actually see the cavity-enabled energy transfer for the homogeneous limit case, and we don't see that in the inhomogeneous limit case. And this can be seen even more clearly if we plot, the different data point that we studied on this delocalization map I showed you before. So here, all those data points are coming from the inhomogeneous limit case, the liquid phase dynamics. So you can see their polariton are all in this phase space of a localized polariton, whereas these three data points are the one for the solid, especially those two just cross the boundary of polariton changing from a localized polytonic state to a delocalized polytonic state. Where the one that we didn't see much of the change in the solid phase is right around the boundary of delocalization. So what that suggests is that there indeed a new delocalization. There should be a delocalization criteria for the polytonic state, where by only satisfying that, the polyton in this energy disorder system can overcome energy disorder and restore its delocalization, and then regain some of the unique properties such as cavity-enabled energy transfer. So this indeed also agree with a prediction by Jianshu Cao's group, by Jianshu Cao himself, actually about 3 years ago, where he predicted that inside the cavity, it can enhance the resonant energy transfer by delocalizing the donor mode. And so through a coherent delocalization of the donor mode by forming polyton, for example, the energy transfer can be enhanced by exactly how many molecules that the excitation is delocalized among all the donor molecules. I see there's a hand there.
We can have the questions after your talk, maybe in 10 minutes.
Okay.
Yeah.
So to summarize this part, I hope that I showed you the role of the energy disorder. So basically, it would deteriorate the delocalization property of polyton. However, to restore, and which is a very important property for polyton, and the way to actually restore it is either to have a really large coupling strength or find out a way to minimize the amount of energy disorder. So with the next 5 minutes, I want to show you an unpublished result and a quick story about how we measure the N. So as you can see here, I hope in this 3 story here, I showed you what polyton really good at to do. That is enable energy transfer between molecule or within molecule. However, there is still a question is that the majority are still the dark mode. So what's going on here? And we want to exactly know how many dark mode are there compared to the polyton. So, but this is a hard measurement because of, we already said that the dark mode are the majority inside of system. And we know through the discussion yesterday, the energy transfer between the dark mode, the population transfer from the polyton to the dark mode is very fast. And as because of the dark mode are the majority, this population transfer channel from the dark mode to the polyton mode indeed would be very, very slow. And we try to measure it through 2D through cross-fix, we can never see it. However, if we can actually measure the transfer, the forward transfer and backward transfer through steady state approximation, we indeed would be able to back out the number of dark mode relative to the polyton state. So we need to figure out a way to measure it. And then my current student Har Spectra, he's very smart, so he can figure out we could use actually proton imaging to characterize the proton by characterizing the proton propagation to measure that. So the idea is the following. If we use the pump pulse to launch a proton, at the very beginning, the proton would just propagate at a fraction of a speed of light until it would decay into the dark mode. By definition, dark mode do not move because it doesn't have the light component anymore. However, so you would expect that the propagation just stop. Okay. However, if the dark mode would populate back to the protonic state, back and forth several times, then we would expect to see a slow diffusion type of motion of the proton after a certain time. So we convert our 2D air spectrometer into an imaging system. I will skip this technique here, but what it allows us to do is to measure, again, we study the tungsten Hess carbonyl protonic system. It now allows us to measure a 2D air spectrum as a function of position as well as a function of time. So this is the full 4-dimensional data, and for example, we can take the spatial distribution of the 2D data at a certain time, and if we take a slide at a different position, we can get the regular 2D spectrum. So this is the data that would allow us to track how the 2D spectrum of the proton, if it start to launch at a specific position, how it would move its position as a function of time. So to summarize the result, this is actually the protonic position data that we measured through this type of measurement. As you can see that after we launch the proton would actually move to the left and then sort of slow down or stop afterwards. So we did the one way to characterize this the motion is to measure the standard deviation of the signal here, and which we plotted here. So as you can see, as we launch the proton would move very, very fast. It's indeed a elliptic motion. However, after a certain point, it's taking a turning point, and then it slowed down. But it doesn't completely lay flat. It indeed still grow, very gradually. So it fit into the second scenario, as I showed you, that after proton drop to the dark mode, it can still seems like somehow pop back. So we developed a model to describe that. Basically, we can launch a protonic system, and then the proton can propagate, it can leak out, it can decay to the dark mode, where the dark mode can also populate back to the protonic state and continue to propagate. So using this model, we first try to fit the experimental data, which is the red curve, without using the back transfer channel. So KDU equals to 0, okay? And this is the yellow curve or orange curve, and you can see this is certainly not a good fit because of the propagation just level off after a certain time. So if we include the KDU here to make it not 0, we can actually fit the data much better, which is the blue curve. So Hars did many of those measurements at all different angles. So what he actually concluded, as you can see from this plot, the number of dark mode versus the proton mode is actually on the order roughly about 10 to the third to 10 to the fourth. So he did all those averaging here, I think is roughly about 10 to the third, if I recall correctly. Nevertheless, it's much smaller than the number that I told you before from a simple theoretical estimate that is 10 to the 7 to 10 to the 11th. What that tells us is that the dark mode are not as large as what people have perceived. So this is the last part of the story that through this measurement of polariton propagation using 2D imaging, we showed experimentally the number of dark mode per polariton is on the order 10 to the fourth. Why this is important? Because back then there were some theory papers that they said even when they have a dark number of dark mode up to 10 to the fourth, they can actually see some modification through the entire polaritonic system. So I think that is where that the hope lies, so that we can have a rational design of polaritonic system. I wouldn't say that we resolve this problem, so we are still a little bit far from actually have a designing principle, but I think we are actually paving readily steps to understand all those amazing results that Eberson and other people have demonstrated in the polariton chemistry emerging field. So with that, I want to just have one more slide to thank the people who actually did the work. This is the full list of my group. I specifically want to thank a few people who actually did the work in the past decade. The whole project started from Dr. Bo Xiang, who's now a assistant professor at Westlake University, did some really heroic works. And then it was taken by my former postdoc, Professor Teng Chen, now a professor at Hong Kong University of Science and Technology, and the former student Zimo Yang. And these three amazing current group member, Dr. Tianlin Liu, Guo Xinyin, and Har Spector, actually took charge of the last two projects that I showed you, and also the funding sources that allow us to pursue this very interesting research direction. And thank you for your attention. I'm more than happy to answer any questions.
Thank you, Wei, for the fantastic talk. So now the session is open for the questions. Hey, Aishwarika, you can unmute and.
Yeah. Hello, am I audible?
Yes.
Hello.
Yeah. Hi. So my question, I have a very basic question, which I was trying to understand. So if I consider a bimolecular reaction inside this cavity, then how do I decide which vibrational mode of the molecule should couple to the cavity mode? I mean, do you look at the rate determining step, or how do you decide that?
Okay, that's a really good question. I mean, the short answer is I don't know. As you can see, I have never actually studied bimolecular reaction for the exact reason. I do not want to step into that complication yet. But I can imagine what people, there are a lot of bimolecular reaction that has been well studied, right? So people would know what is a rate determining step, and they would probably take a look at what is the potential transition state and stuff like that, make some guesses on what are the potential, you can do some calculation to figure out what are the relevant vibrational mode that may actually get involved. But it's so far we've been only focusing on the that one sort of like rotation, a pseudo rotation dynamics, kind of like an elementary reaction that I showed you. It's still a monomolecular reaction. So I think for a while I will just focus on monomolecular reactions to study. But I hope that answered your question. Yeah.
Yeah. Thank you.
Vivek.
Yeah, hi Wei. Very, very cool results,
Hey,
especially the propagation part. So I
thank
had
you.
the anisotropy results were very interesting, and I was wondering about the following. So, let us say in a cavity, I have randomly oriented molecules, but then the ones that, let's say, participate and strongly coupled to the cavity would be the ones that are, let's say, the transition dipoles are aligned parallel to the polarization of the standing wave. And that would reduce n by a huge amount. And this effect is kind of similar to, let's say, if I excite a randomly oriented distribution with a polarized laser field, there's a cos squared theta distribution. Right? So I'm just wondering about this, let's say, pre-alignment because of coupling to the cavity. Do you think that somehow plays into the anisotropy results? Because I'm just thinking about, okay, there is a anisotropic distribution to begin with,
Yeah.
then I'm going, yeah.
Yeah. So So, phenomena, we were worried about that when we first studied it. And phenomenologically, we proved that is not a big deal, because what we did is we just simply measured the anisotropy of the diagonal peak, right? So if there is a huge pre-alignment, I would expect that actually the anisotropy will be 1.
Sure.
But what we measure is actually very close to 0.4. So that means that it's still isotropic. So we were actually quite worried about whether the cavity, the first thing we thought about, whether the cavity the presence of cavity would just change the cross, the anisotropy. But that how we actually verify that is just by checking actually the anisotropy of the diagonal peak. Yeah. So we think it doesn't have a huge pre-alignment effect there. Yeah.
And do you think that, let's say, looking at it the other way, do you think this plays a role in reducing n to, let us say, instead of 10 to the 7, I have like 10 to the 4. And that's because there's only a particular alignment of dipoles, and this is, of course, a fluctuating quantity. But let's say at very early times, there's only a specific alignment of dipoles that really strongly mix with the polariton or with the cavity.
So that's a really good suggestion. So we explore that a little bit. So one thing is that you indeed still need 10 to the 7 to 10 to 11 molecules to reach to strong coupling. If you consider actually the scale or strength of the transition at that moment is rather small, right? So we think what happened, instead of having less molecule actually to be involved in the cavity, the study that we did, is slightly different from Eberson's experiment. We do use a laser to actually excite the cavity, right? So we are not in the single cavity limit. So we actually are pumping many cavity modes simultaneously. And then, if you are providing more house for the molecules, then you just divide it by the number of houses. Then in each of the house, you have less people, right? Yeah. So that is the hand waving sort of intuitive way to think about it. We believe. Yeah.
Okay. Thank you.
Yeah. Sure. Thanks.
Yes, Saurav, you can unmute and. Saurav, you can unmute and yes.
Hi, thanks for the exciting talk. So I have basically like two questions. So like for the dark modes, sometimes there is like energy transfer to the dark modes. And is it like competing with the acceptor modes, or in energy, like when it is influencing the reaction rates, is it like competing? Like, is it good or is it bad, or is it just it is just there?
So the that's a good question. So eventually the energy transfer from polariton, it always transfer to the dark mode part of the polariton. That's basically where all the energy end up to the molecular state. We think what we see is through these energy transfers so far, it's just dissipate the additional driving force for reactions, for example, so that it's been sort of like slow down in the reaction. I don't know if it's good or bad.
Okay. And the second thing is, if the dark modes are slightly bright, as you mentioned, is it possible to directly excite the dark modes? And
Yes.
Okay.
Yes, that's what we see in the 2DR, right? You remember that you see that small peaks in the 2DR. So we can excite it. However, given how big that signal is and how many dark mode there are, the excitation cross section is much smaller compared to the polytonic state, I would say.
Okay. Thank you.
Yeah.
Jana, can you unmute and ask your question? Jana?
Hello, sir. Can you hear me?
Yes.
Yes. Hello, sir. I would like to ask that between a solid versus liquid study you did in the last few slides. Like in liquid, what we are looking at is only one day cavity, right? So whenever the strong coupling is happening, the molecules which are aligned in that directions, like as Vivek sir said, will couple. So, do you think we are not seeing the much effect in the liquids because by the time uh, the reaction is happening, they are realigning and getting out of coupling, and the molecules which are misaligned are aligning towards this one-day cavity and coupling.
I didn't follow the exact question very clearly here, but I think you are asking whether there is a effect as by the time one measuring the reaction that or the outcome of any dynamics, the molecule already rotated out instead of being strong coupled, but it's not strong coupled. Is that the question?
Yes,
Yes,
I think it's asking in the liquid state, you don't see that effect because the molecules already dephased.
That's a really good question. So the molecular rotation for this molecule, I don't remember on top of my head, but it's usually, the liquid phase is quite jammed, so it's on the order of picosecond. If it's 5 picosecond or 10 picosecond, so it's usually much slower. And it's a big molecule, so it has a large inertia. So it would not actually rotate out that fast, we think. Yeah.
so if we take some like molecules with viscosity dependent reactions, we might be able to reduce this. Can we able to reduce this thing?
Uh, we haven't done that experiment. That's a good start. But I think we can, we can do this anisotropy measurement and know exactly what is the rotation diffusion constant. With how big this molecule is, I don't think it would rotate really, really fast.
Okay. Thank you, sir.
Next, Professor Naresh from IIT Bombay.
Hello, Wei. Can you hear me?
Yes. Hello.
Hello. Thank you very much. I really appreciate your talk series, and I personally have a lot of doubts in my mind about this proton-based spectroscopy and chemistry. But I have one simple question to ask. Okay, will it be useful? I don't know. Will it be useful if to map out the potential of a molecule in the absence of the cavity and in the presence of cavity? If one could do an eigenstate resolved spectroscopy.
Yes, I think that's a very, very important area to do. People have but one would do it through high-level calculation, I believe, right?
Because
is that how what you think about?
Essentially, if you look at the IVR dynamics, okay, the change must come from the changes in the potential, the molecular potential by itself.
Right. So if it's through anharmonic coupling, but there is also an additional pathway. I call it IVR, but there could be an additional pathway that is through exchanging of the photon between the modes.
But that's I agree. But then if you look at the molecule by itself, essentially the properties of the molecule itself, if you think if one see, even if there's an exchange, the exchange of one can put it as a perturbative term in the potential, or not rather perturbative. We cannot put it as a perturbative term in the potential. An additional term in a potential is exchange or photon exchange term, and then consider the whole Hamiltonian, and then if you can do diagonalize and do an eigenstate resolved spectroscopy, would it if, for example, if you look at the work done by Lehman and Stolz in 90s and early 2000s, where they looked at eigenstate resolved spectroscopy to understand IVR dynamics. So one would, just in a sense, one would get a similar would be able to get a similar information and about the dynamics that goes on with and without cavity?
I think the challenge there.
No, I know you may not be able to do it, but if in principle, if one could do it.
I'm thinking if that you will get actually because here the eigenstate are just a polytonic state, but the challenge here is that we're dealing with many molecules, so this is a collective regime. So I think this would be a really interesting direction if one could do a single molecule strong coupling. Where that you readily can see basically how one single molecule's landscape been changed to strong coupling. This is still an open question in the field, as there many of the molecule strongly coupled to the same cavity, how each individual molecule's energy been changed. Because if you just simply average out, the coupling strength is super duper small. I think that's what you're asking, right?
I'm not too sure. I mean, I was just thinking in terms of how individual molecules will will respond and change, because what you see is a collective behavior of some fraction of molecules from the entire thing that are. So I was just wondering if one could. I mean, I don't know. I mean, just taking a purist view of re-looking at the potential in terms of eigenstate results. But having said that, I have another question that is kind of related, but I'm not really related. But the other question that I have is that when you look at the upper polytonic state, I mean, when there is a polytonic state creation, you have an upper polyton and a lower polyton. But in most of the spectra, okay, even though not all molecules are coupled to the cavity, I mean, if you have large set of molecules, there is this uncoupled reservoir. Okay. Where is the spectrum of the? I mean, you can see the central peak is completely was missing. So where are the uncoupled the reservoirs?
Oh, where are the signature of the uncoupled reservoir? Yeah, those are also what we refer to as the dark mode. So
but they were initially not really dark. They were initially not very dark. I mean, without the cavity, you can see the absorption right in the middle of the.
You can see. So it's this type of state. Those are the reservoir mode. You can't really see the center one because of just the big reabsorption, so they don't usually can be seen.
And thank you very much. Thank you very much.
Yeah, the reservoir mode is by symmetry. If it's perfect asymmetric, then it's dark inside of the cavity.
Thank you very much.
Yeah.
Thank you, Naresh. Follow me.
Yes. Hello. Yeah, very nice talk.
Hello.
Thank you for the talk. So I have a question on this slide, basically. So you were coupling the cavity mode in between the axial and equatorial mode. Now, what happens if you tune the cavity such that it couples only with some axial mode or the equatorial? Yeah.
Good question. We didn't do that large of detuning. We did somewhat of detuning where that we still can see the effect. But I believe if we detune it only to one mode, we don't see the acceleration. If I recall correctly.
And what was the why do you couple it in the middle? So what was the reasoning behind that?
It allowed the biggest mixing between the states. Yeah.
So that's why
the
you believe that if you couple in the middle, so then the reaction will change, like because it will involve both the axial mode and equatorial mode to mix.
Yeah. You can basically diagonalize the Jens-Hamilton Hamiltonian, and you will see if you detune too much, then there is no mixing between those states in the polyton.
Okay. What is one very basic question? So, what is the difference between this middle polaritonic mode and the dark states?
The middle polyton supposedly, so it's not the dark state, right? Because the dark state is supposed to be here.
Okay. Okay, yeah.
right? The
Yeah.
dark state remain have energy of uncoupled molecule.
Okay.
Yeah.
So the dark states will still be there in this diagram. Okay.
This is the dark state absorption. This is dark state absorption here.
Okay.
Yeah.
Yeah. Thank you.
You're welcome.
Yeah. Next, Dubai.
Sir, I have a doubt. So in the same consecutive way, so the middle polariton and the dark state are really close. Can you really separate out this is coming from middle polariton and this is coming from dark states?
Yeah, we did a cut here. We can see there is a very close peak, and we indeed also I recall. So sorry, this is a while ago. We indeed also follow the dynamics of this guy, and it's actually different. It's probably in the SI. Yeah, we actually
Another
check
interesting
everything.
thing is like you got the dark state number. Can you get the anisotropy decay of those dark state? Like if the number of the dark state populations are in decrease or increase, then the anisotropy also should be.
Yeah, we have that. We didn't feed it. I think it's in the SI if I recall correctly. Yeah. Or no, actually the anisotropy. I don't remember if we did that or not. I think
Because
we
if the
want to
number
do
of the
it.
molecules are less, then the anisotropy decay should be the faster. If any system, the dark states will be the lesser number of molecules or less number of dark states are there.
So you are asking that if we can measure the anisotropy of the dark mode, right?
Yes.
And I don't recall if we did that or not. I think we either did that or we couldn't do it because of the signal to noise for the dark mode. As you can see, it's a much smaller peak. We may not have enough signal to noise. I can't quite remember. Yeah, but back then when we tried to do the experiment, we thought it's also an important measurement. Yeah.
Thank you, sir.
Yeah, Mitali, can you unmute, please?
Hello. Yeah, am I audible?
Hello.
Yes,
Am
yes,
I
yes.
audible? Yeah. So it was very nice talk. So my question is that you mentioned about that homogeneous solid. So since that cavity effects are strong in that homogeneous solid, but those are less in inhomogeneous liquid. So does this imply that reducing that spectral disorder is more important in increasing that Rabi splitting for like enabling energy exchange under that strong coupling?
I think they're equally important because what matters is the ratio between them. In our case, we simply just cannot actually increasing our coupling strength anymore. But one may be able to increase the coupling strength using, a plasmonic cavity, photonic, meta surface and stuff like that. There's many other ways to actually enhance the field.
Okay.
But from a theoretical point of view, they are equally important just because of, what dictates delocalization is the ratio between those two.
Okay.
It's
And
essentially, I think it's like an energy argument there. Yeah. And Jian Shu has actually a paper talking about that even. Yeah.
okay. So, and my other question is on the same lines. So, like you mentioned that n is so much lower than that theoretical value, that 10 raised per 7 to 10 raised per 11 around molecular count. So, is there any particular reason for that the extracted n is much lower than that?
Yeah. So the theoretical number, that's a really good question. The theoretical number is based on the assumption of the cavity, a single mode cavity. That means there is only holds one photon there. So we think in our experiment we excite multi-mode because of the cavity. If you recall from yesterday, it has a dispersion. So then when we use a laser to excite it, we are actually approaching at many different momentums. So we're exciting many of the modes simultaneously. We can actually do some back of envelope calculation to see how many modes that can be excited. And then if you're exciting multiple mode, the number of molecules that are there for strong coupling remain the same, but each of them can strongly coupled to this photon mode and that photon mode and that photon mode, and then when you divided it, it's just like for each of the photonic mode, the number of molecule is less.
Okay.
Yeah.
Okay. Thank you.
Yeah. So Somnath.
Thank you.
Hi, very nice talk. I have a
Thank
question
you.
regarding the energy transfer.
Mhm.
So the axial modes and the equatorial mode, they are collectively coupled to the cavity mode, right? So
Mhm.
you get the coefficient, Hopfield coefficient to understand the contribution of each one of them in the middle polariton, upper and lower. Now I wonder if you selectively coupled either one of them, and then does that change the intramolecular vibrational redistribution to the pseudo rotation mechanism that you observe?
Good question. So far from what I recall, we don't see it. So it's a little bit harder experiment to do because of those are the two vibrational modes from the same molecule. So what we can do is to detune it, right? So if we detune it too far, we don't see the change, if I recall correctly. Yeah.
Okay, so for making these cavities, so I mean, whenever you make these cavities, so you get both of these mode couples together. So you cannot selectively do that. Is there any difficulty in doing that?
Because of this mode coming from the same molecule, so their ratio is fixed, right? So you could actually do. I can only think about two ways to actually control that. One is if one can actually control the absolute molecular orientation inside of system. So you have one of the mode that is aligned, the other one is perpendicular. Then one can do that, but that is experimentally difficult. And then the second case would be if there are two molecular species, and then you can relatively tune their concentration and do it.
I see.
In this system, these are two modes coming from the same molecule. So they're basically coupling strengths are always proportional to their transition dipole moment ratio.
I see.
Yeah.
And their
And
frequencies are also very similar.
that's actually a key, right? So their frequency are separated by something like 30 wave number, and they have to be within that range so that we can strongly couple both of them. If they are separated by 100 wave number, then I can only couple one. Right, so that would be an interesting system to study. If there is to answer your question, if there is a system that the mode are much more separated, and then you couple to one of the mode and see if there is energy transfer changes or the dynamic change, that would be quite interesting. So far, we didn't actually, in all of our system, we didn't see a great effect if we only couple one of the mode. We always have to keep both modes are strongly coupled. However, there is one paper by Lev Chanov from Technion University in collaboration with Igor Rubostov, at Tulane University. They did a 2DR experiment on an open cavity, and they only strongly coupled to one of the vibrational mode. They can still see an enhancement of energy transfer.
I see. Okay,
Yeah.
and one on follow-up is, so in the anisotropy measurement, the mechanism flips, right? You get a faster rate. I mean, and the anisotropy is indicating the IVR mechanism. So
Yeah.
I'm just trying to wrap my head around like what drives this switching in the mechanism. So the pseudo rotation to this IVR. So is there any way we can understand this?
So our hypothesis is that basically the cavity enhanced the IVR. And then so previously the way that IVR dissipates may actually come from coupled to a low frequency mode through anharmonic coupling, and that low frequency mode might be part of the involvement of the pseudo rotation.
Right.
Right.
So that
but
means, yeah. So
yeah, that
inside the cavity, the anharmonic coupling landscape changes, right, between those.
I would say that inside the cavity basically add additional channel to transfer the energy. So it doesn't have to go through the anharmonic channel anymore. It's a competing channel.
Okay.
right? And then it just, changed the anisotropy dynamics. I mean, the pseudo-rotation dynamics. This is purely sort of like a speculation. We don't have any evidence. We cannot actually have evidence from the experimental point of view now. But this is the part that I think really welcome theoretical work to shed light onto it. Yeah.
Okay. Thank you so much.
Thank you,
Thank
Wei. So I have a couple of questions. Like even if you couple these two equatorial and axial modes, so basically those two are orthogonal, right? Axial mode
Sorry.
and the spatially axial
Uh-huh.
mode and equatorial modes are orthogonal.
Yeah.
But if we think about the polarization of the cavity field, how it is coupling to both the vibrations?
Well, so if your cavity mode is like this, they can still do this, right?
Okay.
Yeah. I mean, they look. We are doing a sample measurement, so it's also not necessarily each of the mode contribute to the same amount. It's not always like that. You can have one molecule like this, the other molecule like this. They still only couple. So that's a good point. Yeah.
Okay. So one more thing. So all your experiments are like about populating the polytonic states, but most of the chemical reactions have been reported till now are like in the thermal state, right? In the ground state. So they don't really populate the polytonic states.
Yeah.
The polytonics are just present in the system.
Yeah.
So how do we come to that point from this kind of experimental?
That's a really good question. I don't really have a good answer for it, to be honest. I think to really relate it to the type of experiment we do, one could actually determine how many molecules are populated thermally on the polytonic state and dark mode. And then if we know how the reaction dynamics is changed on those states, one can probably determine whether they have an effect or not. I think we are still quite far, or at least several steps further from actually using those ultrafast experiment to explain the thermal cavity VIC reactions, I would say. Yeah, to some level, you can view those 2D experiments more like close to, the photochemistry strong coupling reactions. I think it might have more relevance to that. Yeah.
Okay. So thank you. One more is like, as you clearly mentioned, taking a single system is the key role to understand that what's happening in the systems. Even we are taking kind of reactions like unimolecular reactions to study. So you don't bring the complications of solvents or any other reactants. So that will be a really key to understand the fundamentals of this field, it seems. So to complex
Yeah, yeah, thank you. Yeah, that's really what we. Yeah, because otherwise there's too many knobs.
Yes, true. Yeah, thank you. So is there any other questions? So if there are none, then
can I ask one more, Kalai?
Yeah, please.
Hi. So for the transport of the polaritonic system, so you mentioned that initially it's a ballistic like, and then it converts to the diffusive like, right? So so is there any contribution of phonon coupled to the polaritonic states initially, which may have giving coherent ballistic type transport compared to more diffusive live or incoherent transport after some time scale? So is there any way we can think about this?
You mean phonon?
Yeah, phonon. Yeah.
That's an interesting thought. We don't see, I mean, in our model, we don't need to involve phonon here because of this is a liquid phase system. So the phonon would be a very low frequency, sort of like modes, I would say. I think it probably would be more important in a solid state sort of polytonic system. Yeah, that's a really interesting thought. We haven't thought about much, but intuitively, I think it probably wouldn't matter. Yeah.
Okay.
But that's interesting. Yeah.
Okay, Jana, quick last question.
Thank you, sir. Like since we can couple only certain percentage of the molecules, can we say if the kinetics is increased by, let's say, X%, it is actually increased by several fold because of only certain amount of molecules are getting affected by the strong resultant kinetics.
So sorry, I didn't quite get your question. Can you
Like
repeat it again?
if there are 100% of molecules, like if we are coupling only 10% of the molecules, and if the rate is increased by 10%, actually the rate is getting doubled because 10% of molecules are getting affected by the strong coupling.
I think you're asking if you imagine average the reaction rate, but if there's only 10% of it's actually really active, then it means the reaction rate of those active molecules is even higher. Is that what you're asking?
Yes.
Yeah, I would say so. I would say that would be the picture that I have. Yeah.
Okay, sir.
Yeah.
Thank you, sir. Thank you for the answer.
Mitali, quickly, last.
Yeah, I want to ask about that middle polariton. So, so does that middle polariton contribute in a measurable way to switching between that hydrogen 1H and 2H hydrogen species?
Oh, that's a good question. We didn't actually study the middle polariton much in that study because, as you can see, it's not there for the liquid phase at all. For the solid phase, is very small. So we didn't do the experiment to specifically pump the middle polariton and see what happened because the middle polariton, is a mixture of both. There was some theoretical explanations of energy transfer back long ago from David Lee's group, where they explained that the energy transfer between upper and lower polariton is through the middle polariton. But there was also, arguments saying that would not be the case because of the middle polariton is also a very low density of state compared to the dark mode. So our intuition is that the middle polariton perhaps is not actually involved in the energy transfer. The energy transfer is more like a direct energy transfer from the lower and the middle from the lower to the upper polariton, mediated by the fact if you think that the upper polariton is a donor, the lower polariton is acceptor, that the polariton is delocalized, so that's why that is enhanced basically. So it doesn't have to actually go through this middle polariton.
Okay. So, okay.
Okay. Thank you, Mitali.
Okay. Okay.
Yeah. Thank you. Sorry, wait for that long discussion session. We really
thank you.
appreciate.
Yeah, really enjoyed it.
So yeah, so already we had enough questions. So it's a time to thank Wei for this fantastic series of talks. So we are really thankful, Wei, for taking up this invitation and your engaging discussions. It's really nice to have you here. So we really, the Department of Chemical Sciences, TFR, would really like to have you as a friend for the long-term interactions and discussions. It will really help us and can have enough scientific discussions in the later state also. We are really looking forward to host you in person in TFR Mumbai. So maybe in the coming year, we definitely will make this to happen. Thank you very much.
That's great. Thank you so much for having me. Yeah, I look forward to meet you guys in person in the future.
Yeah. So JD wants to convey
thank you
his
for coming.
real appreciation as he is not available here. So he just sent a message to convey his regards so that he could not be here. But yeah, thank you very much. Thank you.
Thank you. Yeah, please pass my regard to him as well.
Yes. Thank you. Thank you.
Thank you, Clay.
Yeah. Bye.
Thank you, Vivek.
See you later. Bye.
Thanks to all the
Bye.
audience for being here till the
Yeah.
last.